What is computer? How computer work? Why computer do thing? I'm going to explain all of that and more in this video. Computers are just machines that follow instructions, specifically to read, write, and erase some data. And by data, I mean ones and zeros. However you manage to represent them, if you can make a machine that will read, write, and erase those ones and zeros, then congratulations, you have a computer. You can make a computer out of ball bearings and wooden tracks, out of pipes with water flowing through them, out of wires with electricity flowing through them, or literally billiard balls, I'm not kidding. You can even make a computer out of a wooden frame, a few strings, some beads, and a sentient life form. As long as you have some way of storing information, typically something that represents a 1 or a 0, on or off, true or false, full or empty, and some way to manipulate them, you have a computer. Put these ones and zeros together, and you can represent numbers. We normally count in what's called base 10 because we're primates and we have 10 fingers. However, you can actually count up to over 1,000 using your fingers in binary. Binary is what happens when we count using base 2 numbers instead of base 10. In base 10, we can only fit up to 9 in the ones place, and if we add one more, then we have to put a 1 in the tens place and the 0 in the ones place, because we have 1, 10, and 0 ones. If we change the base of our counting system, we change the value of what 10 is. For instance, in base 6, we would only be able to fit 5 into the ones place, and when we get a 6, we would represent that as a 1 in the sixes place and 0 in the ones place. In binary, or base 2, we can only fit 1 into the ones place. Adding another one gives us 2, which is our base. So 2 in decimal is 10 in binary. You may have seen this on a t-shirt. Any number we need to represent, we can do by adding powers of 2. So this is how you can count to over 1,000 using just your fingers. If your thumb represents 1, then your index finger is 2, and your middle finger is 4, ring finger is 8, your pinky is 16, and on your other hand, your other pinky becomes 32, then 64, 128, 256, and 512. Add them all up and you get 1023, which is one less than the next number would be, if you had 6 fingers on one of your hands. So for instance, 1, 2, 3. In addition to numbers, you can use ones and zeros to represent letters of the alphabet. For instance, you may have heard of ASCII. First published in 1964, ASCII is a standard computer alphabet, which means it defines how letters can be represented as numbers in a computer. ASCII is actually based on telegraph code, so the ASCII alphabet was originally designed to deal with telegraph signals and typewriters. As such, the ASCII alphabet includes characters that represent things other than letters, like punctuation, spacing, and instructions to scroll the paper, line feed, and to return to the left side of the paper, carriage return. These are called special characters. Some of them only represent instructions to the typewriter and don't actually represent characters like letters or numbers. The carriage return, CR, and line feed, LF, characters are often seen together as they represent instructions to start a new paragraph. You may have seen this symbol on the Enter key of older keyboards. This represents the CR-LF action, which is why the Enter key takes you to the start of a new line. So, now that we have a way of representing numbers with ones and zeros, or on or off states, a computer needs a way to decide which wires or pipes or redstone paths to turn on or off. This is where logic comes in. Logic gates are mechanisms that determine some output based on 2 inputs. The basic gates are AND, OR, XOR with the exclusive OR, NAND, NOR, and XNOR. Any mechanism that can accomplish these can function as a logic gate. You can do this, for example, with redstone in Minecraft. These are some logic gates I built in Minecraft. Each one has 2 inputs and 1 output. The output is either on or off based on the configuration of the inputs. This first one is an AND gate. The output is only on if input A and input B are active. This is an OR gate. The output signal is active if either A or B is active. This is an XOR gate. It's similar to an OR gate, but it's a little more complicated. The output here is only active if one of the inputs is active, but not both. This is a NAND gate, which is the opposite of an AND gate, which means the output signal is on unless both inputs are on. This is a NOR gate. It's the opposite of an OR gate. This one gives out an output signal only if neither input A nor input B are active. This is an XNOR gate. It's the opposite of an XOR gate, which means that the output signal is active as long as the input signals are the same. You can combine logic gates to do things like math operations. This, for instance, is a binary adder, which means it'll add two bits together, A and B. It also has a carry bit, which means that you can chain these together to add together larger numbers. So for instance, if both of our inputs are active, then A and B, this gate turns on, which represents 2. So we have a value of at least 2, which means we need to carry a 1 to the next place. If only one of our inputs is active, then the AND gate is false, but this XOR gate is true. This means that exactly one of our inputs is turned on. This is also referred to as the half sum, because it means that our inputs add up to 1. If we also have a carry bit active, then that 1 adds to this 1, and again we get 2, or the carry bit is active, which means we need to carry it up to the next place. The last piece of logic is this carry XOR half sum gate. The way this works is we either have the carry bit active or we have a half sum. Either way, it's going to be an odd number, so we'll activate the 1 whether or not the 2 is active. When you have to carry a 1 to the next place, that becomes the carry input for the next adder. And of course, you can chain these together to add numbers of any size. This is a binary counter. Each block counts a 1 or a 0, but they can be chained together to represent larger numbers. Every time a counter block receives an input signal, it flips on or off. So for instance, this is the 1's place, and if I press the button, it'll turn on. If I press the button again, it'll turn off, but it will send a signal to the 2's place, and the 2 will turn on. If I press the button again, now I have the 1 and the 2 active. One more time, it activates the 4. So I can keep going here, and now it's activated the 8's place. So I press the button 8 times. So now all the lights are on, all the bits are showing a 1, which means we have 8 plus 4 plus 2 plus 1, or 15. So what happens if I press the button again? This is called overflow. I'm trying to store a number that's larger than I have space for. If I had another cell right here, this could represent 16, and that light would be on right now. But since I don't have enough room, it's flipped back to 0. These are some different clocks you can use to keep track of time. This is a 5 clock that uses 5 torches to turn a signal on and off every 1 second. This is a pulsar, which rapidly turns on and off, I think, every other tick. Real-life computers use something called a quartz crystal oscillator, which is basically a tiny circuit that bounces a small amount of electricity back and forth using a crystal as kind of like a spring. As long as you keep supplying a small amount of electricity, it can keep going indefinitely. This is also how quartz watches work. This is a type of memory cell. You can use this to store 1 bit of data. To write a 1 to the memory cell, you activate the write input. Then when you activate the read input, you should get an output of 1. If you clear the memory cell, then when you read it, you should get an output of 0, meaning you don't get an output. This is another type of memory cell. It uses a slightly different mechanism to store a 1 or a 0. Again, if you have nothing stored in the cell and you activate the read input, you will get no output. But if you write a 1 to the cell, then when you read the cell, you get an output signal. And again, we can clear the cell, and when we read it, we get no signal again. These are all the basic pieces you need to make a computer. Anything you could use to make functionally similar components could be used to make a computer. Steve Mould, YouTube channel Steve Mould, made an adder with water-based logic gates. Matt Parker made one out of dominoes. Combining these basic elements can create a processor, which is the heart of a computer, where the math and logic happens. A processor typically has several pieces, including the ALU, or Arithmetic and Logic Unit, which does basic math and logic operations, a control unit that manages communication between the different components, several registers that hold small amounts of data temporarily, buses or wires that carry data from one place to another, and a clock signal that coordinates all the actions between these different components. Different processors can be made to specialize in doing different kinds of math, or using machine learning, or being really fast with specific operations, etc., but the basic structure is the same. Processors can perform all the logic operations a computer needs, but they don't store very much information. They just keep whatever few bytes they're dealing with at the moment. Storing information is handled by memory and hard drives. Alright, so we've talked about representing numbers and characters with binary code, but they can also be used to represent instructions. Early computers had to represent every instruction as a number, and those instructions were listed in order in the computer's memory. The computers that took the Apollo rockets to the moon worked like this. The instructions were programmed directly, physically, into the computer memory by weaving wires into ropes. The ropes were covered with metal rings, such that wherever a wire is threaded inside one of the rings, it counts as a 1, and if it's outside, that counts as a 0. Each wire in a rope can then contain a different series of 1s and 0s to refer to machine instructions. This work was performed by mostly older women in factories, earning the nickname LOL memory, or Little Old Lady memory, which is cute, but it also kind of diminutizes them and downplays the importance of their work. This was really tedious work, and it was essential to the Apollo missions, and many of them were not very old. Modern computers use memory as a way to store information temporarily. You may have heard of RAM, or random access memory. This is just open space that the computer can use to store temporary information on the fly. The memory is not used in a predictable way. Information is stored wherever space is available, hence the name random access. There are two different types of memory, stack and heap. Stack memory stores an ordered list of variables in a small fixed size, managed automatically by the system. It's a last-in, first-out data structure, meaning that the most recently used memory block is the first one to be freed up for use again. If the stack fills up and the system has nowhere to store new variables, this is called a stack overflow error. Stack memory variables can also refer to the addresses of data stored in heap memory. Heap memory is how larger data values and structures can be stored. A program must tell the computer how much data to store and where. This can also be done automatically using data objects in programming languages. Heap memory is accessed randomly and does not have to fill up in order, unlike stack memory. Heap memory can therefore be dynamic, since blocks in heap memory can also point to other blocks in heap memory. This gives data objects a hierarchical structure. Permanent or semi-permanent information is generally stored on hard drives, which store these 1s and 0s in a more stable state. In general, the difference between memory and a hard drive is that information in memory is temporary, situational, and quick to retrieve. Hard drive information is intended to be long-term, generic, and large, which means it can take some time to retrieve it from storage. Thus, hard drives tend to store larger amounts of data than memory. In RAM, memory is typically stored as a small amount of electricity trapped in a tiny capacitor. RAM is also designed to lose information when it loses power. Hard drives, on the other hand, are designed to retain information for a long time. Disk drives store 1s and 0s by flipping tiny magnets arranged into sectors on a disk. Solid-state drives trap electricity like in RAM, but the charge remains in the bit after the computer is powered down. Quantum computers store information a little differently. Instead of 1s and 0s, they store 4 superposition states, and so they also have their own logic gates that work a little bit differently. You can also do all the math and logic operations that you can do with binary computers using logic gates and qubits. I don't know exactly how these work, but I know they can accomplish the same thing, even doing multiple computations simultaneously with one operation, which is like multi-threading but turbocharged. In general, computers have the ability to store and process information, but how they do this is a matter of programming. Programming is when you use information stored in the computer in order to refer to instructions that the computer can carry out. As mentioned before, these instructions can be predetermined and built in, so-called machine language. Or these instructions can be referred to using assembly language, which is designed to be a more human-readable set of machine instructions translated into machine code. Machine code is a set of numbered instructions that are actually physically programmed into the circuitry of the computer. Assembly language commands can then be grouped together to make more complicated procedures, and those procedures can be grouped together to make even more complicated procedures, and so on. This is how modern, high-level languages have been developed. The first commercially available programming language is called Fortran, or Formula Translation, developed in 1957 by a team at IBM. Other early languages, still used in some applications today, are Lisp, COBOL, and ALGOL. Most of these early languages use punch cards, or physical pieces of paper that you would program by punching holes in the paper. BASIC, or Beginner's All-Purpose Symbolic Instruction Code, was designed to be written using a keyboard and accessible, as the name suggests, to beginners like engineering students. The C programming language, which followed earlier attempts A and B, was designed in the 1970s by Dennis Ritchie to be a high-level language, and is now considered to be a relatively low-level language, that uses more human-readable syntax to machine instructions. C has since been used to create many higher-level languages that turn sets of C instructions into complex but easy-to-understand instructions. Such languages include Java, JavaScript, C++, Python, and many more. So how does that work? How do you get a more complicated language from a simple one? Well, you write a bunch of code in an existing language that describes how to translate your new language into the existing one. This set of code is called a compiler. People have written compilers for all sorts of interesting new languages, like Piet, which uses colored squares, Chicken, which uses nothing but the word chicken, seriously, Velato, which uses music notes, that's neat, and even Klingon, although the closest it can get to Hello World in Klingon is What Do You Want Universe. So once you have a programming language, you still need a computer that can read it. This has to be done by software which can translate whatever language into machine instructions in the actual computer circuitry. An operating system is software that you put on the hard drive of a computer that's capable of organizing file storage and running programs. So, how do we actually tell what any of these ones and zeros are? How do we put them into the computer, and how do we get them out? Input and output is primarily handled by what are called peripherals. This refers to any hardware outside the computer itself that the computer uses or interacts with. This includes keyboards, mice, cameras, printers, monitors, speakers, and so on. The computer needs to know how to communicate with these peripheral items, and they need to know how to talk to the computer. That's why computers need pieces of software called drivers. Drivers have sets of instructions for communicating with a particular peripheral. Most modern operating systems come with a whole bunch of generic drivers already installed, so you don't have to worry about it. But of course, it depends on the peripheral. The less common it is, the more likely you'll need to install software to get it working with your computer. The first peripherals were typewriters, although digital displays have been part of the computer itself since it evolved from simpler lab equipment with screens like oscilloscopes, which were used to create the first video games, in fact. The input for these was typically buttons and knobs that were hardwired into the machine itself, and thus technically wouldn't really be considered peripherals. The mouse was invented a lot earlier than you think as well. It was conceived of by Doug Engelbart and first built by Bill English in 1964 at SRI International, a non-profit scientific research institute. Doug introduced the mouse to the world in a computer tech demo nicknamed the Mother of All Demos in 1968. This impressively prescient demo also involved remote shared access and even video communication, demonstrating quite accurately the future of computer interaction. Most mice now use optical sensors instead of a trackball, and use radio signals to communicate wirelessly with the computer, but the basic principle is the same. Building a computer today requires all of these components together. To build a computer, you need a processor, a motherboard capable of holding that type of processor, memory that will fit that particular motherboard, a hard drive, a power supply to supply all these with electricity, and a case to put it all in. You might also have a separate processor and memory dedicated specifically to processing video, called a video card or graphics card. Often the case will come with some LEDs and a few fans, or maybe even a coolant system. A processor has electricity moving through it constantly, so it heats up easily. Keeping a computer cool keeps it fast and healthy. Finally, if you put it together correctly, then all you need to do is load an operating system and whatever software will work with it. So where are computers going? Why are we doing all this? Will we eventually have to fight a war against them because they've become so intelligent they decide they don't need us anymore? Will we end up in a Dune universe where all computers are banned? Or a Matrix prison? Or a Wall-E space resort? Or something else? It's always something else. I don't know where the future is going, but I do know that understanding the future will require understanding computers.